I'm Dominik. I'm working for Polygon Labs now. We are called Polygon Labs. And I'm working for Polygon Miden. So we have different products, basically. We try to do everything with zero knowledge now. And Polygon Miden is a zero knowledge rollup that tries to extend Ethereum's feature set. Whereas I'm sure you're more familiar with the ZK EVM or other ZK EVM solutions, and they are like straight scaling solutions, meaning that they offer the exact same feature set of Ethereum, just to more users and cheaper. So our goal is to build a rollup that extends Ethereum's feature set, and we think that enables novel and useful applications that are currently not possible by some limitations of the EVM. So we thought about, before all our moms would use Ethereum still. We think it should scale better, it should be safer and have more privacy. But what we mean by that is it should have the ability to handle high load over an extended time. It should have less human error and attack surface. So if you lose your private key, or my mom would lose it, then there should be some way to recover it. And obviously, there should be some sort of privacy, at least at the level of PayPal, but maybe more, before my mom would start using it, I guess. And so we try to add new features in that dimensions. And basically one design, a key design of our rollup is that users can create zero knowledge proofs as distinct actors. And this is super different to the EVM, and I will explain in a minute. But basically, the ability that for users to create zero knowledge proofs means that every transaction only gets executed once. So the network only verifies. Whereas in a normal blockchain, obviously, we verify by re-executing or recomputation. And we try to send only proofs in the network, and that we think scales better. And if the users can act distinct from each other, like logically independent, we can execute transactions concurrently, which gives us better scaling properties. For example, or like we aim to have parallel transaction execution. At the safety dimension, we have basically a transaction model, which I will explain in a second, that helps us or allows us to recall transactions. And that means if I send a transaction to an address that doesn't exist, or I change my mind, then I can get it back. And obviously we have account abstraction, which you probably know, that gives you social recovery, key rotation, rate limiting. But in our model, assets are also stored within the account. So there is no global ERC20 contract, for example, that stores who owns how many of these tokens, but we store every asset in the account as a feature. Okay, and for privacy, so we use zero knowledge in the real sense of zero knowledge proof. So not only for validity reasons, and so users can basically hide account data in our model, and they can selectively reveal state. And one bonus is that there is no extra cost for privacy associated with that. And in addition to that, we can also hide the transaction graph or the transaction data. And first, we will have Web 2 privacy, meaning that it is private from other users, but eventually we will get to a fully private solution. Okay, so that's a lot of promises. How do we do it? Basically, because we don't follow the EVM path, we have created a Miden VM, which I'll show you in a second. We are not bound by the account model that Ethereum uses. So we basically mix together an account model, an UTXO model, and zero-knowledge proofs to achieve exactly the features that I just described. So it's an actor-based model, basically, with concurrent off-chain state. That's enough with the buzzwords, but let me explain. Who is familiar with the actor model? No, someone? Yes. It's like it's used with distributed databases, and basically actors are little state machines with inboxes. So when you think of a system, and then you have these actors, every actor can change its state independently from each other, and they can send messages to each other. So they communicate by message passing, and every little state machine or actor has an inbox and receives a message, and when it decides to change state, then it can create other messages and trigger state changes with other actors. This is used in distributed databases, and this basically motivated our design for our zero-knowledge rollup. And a key property is that messages can be produced and consumed asynchronously. And this is how we try to get concurrency. Okay, so the actor model in Miden means we also have accounts in Miden, like on Ethereum. On Miden, every account is a smart contract, so it has a state and an interface, some code. And these actors, these accounts, basically, they send nodes to each other. So the messages from the actor model now are just nodes, like bank nodes, and both can carry assets. So an account has assets and a node has assets, and you can send assets to each other with two transactions. So that means the first transaction means that the account 1 would create a node and send it out. And at some different point in time, account 2 can consume the node, and then the asset transfer is complete. And this is that means the transaction is actually quite different than on Ethereum, because a transaction always involves only one account. It is defined as the state transition of a single account. And it changes its state when it consumes nodes and or it produces nodes. And that's how the transactions basically are distinct from each other and can be proven distinct from each other. So basically, like you can execute a transaction and consume several nodes in it. So you can consume the node by consuming the script, reading the script of the node. And in that case here, for example, the account receives something from node 1, and then it consumes node 2 in the same transaction, receives another asset, and then it can finalize it. And because we are zero-knowledge rollup, we can try to prove every transaction, or every transaction at the end is being proven. That means that like a transaction is a state transition, and we use the Miden VM to create a Stark proof for exactly that transaction and can prove the correctness of this state transition. And because every transaction only involves one account, we can do that in parallel. And it's even so that users can do that themselves. And that's how it scales. So basically, we have these two transaction modes. A transaction needs to be prepared, same as in Ethereum. Someone needs to define the structure of the transaction and which asset should be there. It needs to be executed. It needs to be proven in our case. And then we have this final object, the transaction proof. And so the execution part and the proving part can be done by the operator. This would be the same as in any other zero-knowledge rollup out there, like in the ZK EVM, like there's a centralized prover or a small set of centralized provers, and you send them the transaction and they execute it and prove it. And on Miden, we also have this local transaction execution. And this basically means that the user himself can execute the transaction, apply a state transition, prove it, and send it to the network. And the network or the operator only verifies that something correct happened. And now we combine this with you have the ability to store your data with the operator, like your full account data, or you can only store a hash of your account data there. And this is how we get privacy. So even with the hash, you can verify a proof against it, but you don't know what happened in this state change. And so we end up with actually 4 modes of transaction. So when you have a network execution, so the operator executes and proves, and you have on-chain data, then this is like on normal zero-knowledge rollup. But if you have, for example, in the bottom right, off-chain data, so I store only the hash of my account with the operator, and I locally execute and prove my own state transitions, then I'm basically a layer 3 on the Miden rollup. So basically every account is a zero-knowledge rollup itself. So because I can prove my state transition, and then only that gets updated when the proof is being verified by the operator. These proofs that can happen in parallel can be locally or network, as I said, and then the operator batches them together. This is similar to other zero-knowledge rollups, but at the end we need to roll stuff up or batch it together. So we have recursive verification. We have batch proofs, and they get then batched together into block proofs. And the upper part must be done by the operator. And this then actually, like we batch that together into epochs, and then this gets updated to Ethereum at the end. Yeah, and I want you to try it out. So if you can, I don't know if it's too far away, but you can click on that. And then you should end up in the Miden playground. So this is the Miden VM in the browser. And it looks a bit weird, but when you scroll down, then you see a very small assembly program that adds 1 and 2 together. But at the bottom, like at the top, you have the button proof. When you click on proof, then you basically prove that the Miden VM executes this program, that it adds 1 and 2 together, and it should be in less than 1 second. Yeah. Is it in less than 1 second? Yeah.
No, 2 seconds.
2 seconds, damn. Okay, and when you now verify, it should be 1/10 of this time, roughly. Yeah. Right? Okay. And this is like how it would work. So obviously a transaction is a bit more complex as a program, but like our goal is also that people can, in theory, on a mobile phone or on their laptop, create these proofs, send it to the network, and then the network only verifies the state transition. Like obviously there are, you can choose the network execution or local execution, and like when a transaction touches public state, that's a bit more complicated. So when I just send some money to Franzi, for example, then it would only involve my account in my transaction and Franzi's account in her transaction. But imagine I would use a Uniswap-like smart contract, and I want to swap something. And then this is somehow shared state, so other users must know that something happened and actually what happened, because the price changes. And then it is a bit more complex, but I can show later that at least one of these transactions then needs to be a network execution. Local execution obviously can be private, whereas network execution not so easily, but at least you get privacy against other users. And the hardware requirements are high and low, obviously. And a cool thing about Miden is the fees should be much lower when you prove it yourself, right? Because this is resource intense. And that means the more private Miden will be used, the cheaper it gets, or the better it scales. And this is actually quite nice and a bit different to what we have seen from other rollups so far, there where it gets more expensive when you add privacy to each other. Yes?
How much cheaper would it be?
That's a good question. So we don't have a gas schedule or a gas model yet. So yeah, but like it is
10 times cheaper, 2 times cheaper, 100 times cheaper.
Yeah, like I cannot really so the proof verification grows logarithmically and needs way less resources, obviously. And proof creation is quite resource intense, but I do not know, I could not answer how much cheaper it would be yet, but maybe in 2 months, hopefully.
But also not like, vaguely speaking, like 100 times or 2 times cheaper.
It's not clear yet on Miden how we charge actually, so like how gas looks like. So I could not really tell. So and our goal is to basically create this design space for novel applications. And so basically in a general rollout, you have higher TPS than on Ethereum and cheaper transactions. That's the goal of scaling in a very short. And we add client-side execution and proving, so our clients can create the proofs, which is quite a nice feature and gives you that you can even run complex computations, so you don't have a gas limit because the proof size doesn't really grow with the complexity of the program. And you have these flexible transaction modes that I've shown. You have off-chain data. So basically, I can create my own little layer 3 on Miden for free. And I have updatable transactions, meaning that I can create a transaction and update it for free, which is quite nice. For example, when you think of an order book exchange that you want to have on-chain, I can create an initial transaction, and then I can keep updating it. And this is, I can show you. We also have recallable transactions. So when I send something to the wrong address or to an address that doesn't exist, then I can consume it myself after a certain time. So let's think of an order book exchange, for example. This is one of these novel applications that we want to have on-chain. And for an order book exchange, obviously, you need to be super cheap because like this order book gets updated many times in a second or like in a certain time period. And if you would pay every time to update this order book, then it's just not feasible. That's why we have these AMMs, basically. And on Miden, I show you how it could be done. A node in Miden is this message, as I explained before, that gets sent from one account to another and can carry assets. In this case, the node has 100 ETH. And the node does not only have an asset, it also has a script. And this is the script that gets executed. Whoever consumes this node needs to execute the script. And our scripts and programs are written in like a Merkle tree structure, like we call it a must structure. And basically, I can create this node with this Merkle tree and commit to a certain code. And then I can say at the beginning, whoever consumes this node gets the 100 ETH from this node, but he needs to create 1,000 DAI, like another node with 1,000 DAI and send it to me. Okay, and then people can say, okay, I don't take it, that's too expensive. And so after a certain period of time, I can say, okay, whoever consumes this node gets the 100 ETH, but needs to send me 500 DAI. And hopefully, like this second thing is for free and almost in no time, because I just need to reveal another part of this Merkle tree. And it does not need to be on-chain. And then if no one takes it, I can just consume the node myself. Like other examples could be cool incomplete information games because I can hide basically moves. And I can, if you have a complex on-chain game logic, you can build it on Miden because it's not expensive anymore if you do client-side proving. Basically, you don't pay gas. When I create the proof myself and send it for verification to the network, I can run fairly complex programs, and they are super cheap. And obviously you get the privacy part. So you could create a cool on-chain game. And sovereign wallets could be interesting as well. So I could, like obviously with account abstraction, you have super powerful wallets, but on Miden, you can hide parts of the wallet and reveal it to some people, but to others not. For example, to, I don't know, compliance or auditors. And that means you can have like a wallet that, I don't know, is hidden from competitors, or when I'm a crypto founder crew, then maybe it's good and I don't get hacked as much, and not everyone sees that I have 10,000 ETH in my wallet.
How do the private transactions work with respect to the data availability? Because if you submit the hash, you can of course make a proof, but then how did the other nodes actually know who sent what to who?
Yes. Like the data availability question in Miden gets pushed to the user. So if you want to use Miden privately, then you can basically store the data encrypted on Google Cloud or on any other program. But if you lose it, then the operator or the network would not know how to reconstruct that state if they only have the hash. If this is your question.
Yeah, kind of. But more other people have more questions.
Hi, I just have a follow-up question on that. So you said before that the user could choose when to send data. Is that correct? So like for every transaction, I would just choose what data I send?
You can choose the transaction mode. So you can choose to execute and prove the transaction yourself, or you can just send the transaction to the operator, and the operator would execute and prove it.
And what would be the case? Well, like, why would I decide to actually send data? Is there like a use case first?
For example, 1 second. So imagine you have like this setting, like 2 accounts in a Uniswap like smart contract, right? So and then account 1 wants to trade, and account 2 wants to trade as well. So they would execute a transaction. They can do it locally and send a node to that smart contract. But now the smart contract, because node 1 or node 2 would change the state differently, needs to have a network transaction execution and proof by consuming both nodes at the same time and creating 2 nodes in the same transaction. And this transaction 3 basically needs to be a network transaction, because if not, transaction 2, node 2 could not be consumed anymore. So if you have transactions with public shared state in that sense, you always need to run a network transaction. I hope this answers your question.
Does that mean then that all the smart contracts, sorry, it's very naive, but does it mean that all the smart contracts basically have to be like updated for this? To just kind of like to decide whether it's a network transaction or not, like so that the user is basically forced to share data?
No, like on Miden, everything is a smart contract, basically. And but you would, like when you code your smart contract for like DEX or so, then you would basically need to know this needs to be a network transaction or not. Yeah, but it can also be that you have your own prover and sequencer of that smart contract that is somehow public.
Sorry. Thanks. My question is about ordering. Now, I understand when you're just sending assets between accounts, then it's just local updates on the accounts to accept or to send. That can be done in parallel. But once you have nodes that could be consumed by different nodes, then ordering becomes important. So you need some kind of a global consensus mechanism within this rollup. So that kind of makes it we're no longer parallel. So how does this ordering work? How do you decide what needs ordering and what kind of a consensus system, or how does that happen in Miden?
Yes. Like if I understand your question correctly, then exactly that, in that example, you need to order node 1 and node 2, right? So one of those you need to execute first, but because it's in one transaction, basically the ordering happens in whoever executes this transaction. So the transaction.
No, I meant like, suppose you have one of those Merkle tree diagrams you had before, and there's a note out there, and it could be consumed at 2 different accounts. Like, either you consume it back yourself to claim it back, or somebody does accept your trade offer for the 1,000 DAI and consumes the note, and they can't both happen. Like, this note can only be consumed once, but we don't know which account will consume it, so we have to decide which one of the 2 happens, so there needs to be a global ordering for that.
Yes, so maybe I understand your question correctly now. So basically there is a UTXO database where you, basically when you create a node, you add an entry. And then there's a nullifier database that basically has an entry if the node is already consumed. So if 2 accounts at the same time want to consume a node, then it depends which,
So you need consensus on the UTXO database.
Yes.
The global, that's what I mean.
Exactly. Yeah, okay, now I get your question. So I don't know yet. At the beginning, we have a centralized operator, but there must be some sort of consensus mechanism exactly on the state databases, UTXO, nullifier, and account.
Cool.
Yes.
I'm not sure if you have talked about this because I was slightly late. But have you decided on what programming language you're going to be used for creating smart contracts?
Yes.
In Miden?
And the answer is because we don't go with the ZK EVM, Solidity is quite hard.
Right, yeah, because I see some new opcodes there, yeah?
And so at the moment, we have our own assembler language, Miden assembly. But we know that this will be quite hard for people to learn. So we have a compiler team that basically, at the moment, we implement Sway and move the smart contract language from Facebook. And these are easier with our model to implement. And in the future, hopefully, we will have a Solidity transpiler. But I've just heard yesterday that Nethermind, they tried to do that for Starknet. And they seem to have now decided to keep Cairo 1.0 and not use this transpiler. But yeah, we'll see. At the moment, it's Miden assembly and then in October, when we have our public testnet, we aim to have a move compiler.
And Sway, you said, as well?
Yes. Okay. Sway, like a subset of Rust or Sway.
Like from
Fuel VM, exactly. Yeah.
Is it late, Francie? What aggregation proof system do you guys use?
Pardon me, which
aggregation? The aggregation proof system?
The Miden VM uses Starks. Yeah. And we have recursion in that we built our own, basically to verify within the Miden VM a proof and create a proof for that. So does that answer your question, or?
Kinda,
maybe.
But we're not using Plonky, right?
No, it's Stark. So
but because
will be Starkey.
Because what Plonky uses a Starkey for the first transaction and then aggregation Starkey 2, right?
Yes.
So do you guys do something similar, or?
We don't.
I understand you're a different team from Polygon Zero. So
exactly, but we work together.
I'm just wondering how similar.
Yes, we all use the same prime field, like the Goldilocks.
Okay.
But we don't use Starkey yet. At the very end, for the last proof, we also think of using FFlonk, like the ZK VM at the moment. Yeah. But we don't use Starkey yet.
So is it more similar to the Hermes backend stuff with the eStark thing? Okay. Is it the same?
No.
eStark?
No. We use basically from the Winterfell. I don't know if you know that. That was what Bobbin created. Like the sterilized Stark prover. And it's pure Stark so far. Yeah. So whereas the ZK VM, they have a Stark at the end. Yeah. But we don't have an end yet. So maybe in the future, yeah. And then we use deep fry and I can send you some documentation after that, but I'm not sure if I can answer the questions on the VM.
Yeah, thank you.
Hey, thank you so much for the talk. I learned a lot. I was just wondering if you have any like special new security concerns now that the playground has widened significantly. If there are any new dangers lurking in the dark, maybe.
You mean security when you use?
Yeah, I'm a white hat, so I just wanted to know like where where am I supposed to look? Or
yeah, that would be interesting, and maybe that goes too deep. But yeah, in Miden, like as I said, we store assets within the account, so that could be interesting, like how the attack vectors would look there if you don't have a global ERC20 contract that can be hacked or any other global contract, and yeah, obviously, like we are too early in the process to answer that question, I would say. So at the moment, we have the VM running and it's optimized, and we are building the rollup, like the client in a node. But it would be interesting to talk to you in August or so, when there's more than just a theoretical idea on how to build smart contracts and how they interact.
Cool.
Yeah.
Are you planning on like launching a bug bounty program maybe on Immunify or something?
Definitely, yeah. Like Polygon did with the ZK EVM, we will do the same. Our roadmap basically is in October you should be able to use it. In December we hopefully have cool new apps that we can have as a showcase, and in end of March next year. So we hope to have mainnet, and also mainnet is not 100% certain if we will be a standalone rollup or somehow integrate with the ZK EVM or the other Polygon products.
Okay, so yeah, that's all I wanted to know. Thanks.
So did I get you right that at the end there should be a centralized entity or whatever, how you call it, which summarizes these transactions? Did I get that right now?
At the beginning, exactly, like at the beginning, we also have a rollup with training wheels like the others. And at the beginning, we need to have a centralized operator also for debugging purposes. But Miden actually, as I explained it here, is quite suitable to be decentralized. Like we need to think of a consensus mechanism, obviously, but we have a nice way to mitigate state bloat, and basically, if we have more operators running, then not every operator needs to know the full state. And that could help to really decentralize it. But to your question, at the beginning, it will be a centralized operator run by Polygon Labs. And hopefully 1 year from mainnet launch, we go to a more decentralized setting.
So which means, so at the beginning you have one centralized authority, then it might be 2, then 4.
Most likely,
then maybe you have 1,000 or whatever. But at the end, it's not going to be like everyone. So not like decentralized. So we're just like it is a decentralized idea which you give here, but at the end it's not decentralized, but like there's a set of centralized authorities.
Yeah.
So at the end, it makes not like that much.
That depends, I guess, how you would define, and that's a super interesting discussion indeed, how to define decentralization. So it could be still decentralized if everyone can verify proofs, and when you have these escape hatches on layer 1. But you're right, so not every player or actor in Miden is equal. So yeah, but at least our clients can create their own proofs, which is a good step forward. But yes, you're right. Yeah, and but this is I think a real decentralized zero-knowledge rollup. At least when we go from the Miden design, will take at least 2 years or so to be there.
I was just thinking about this as it relates to what it might mean for cross-shard composability, if that makes sense, as it relates to having operators kind of take care of state across different users or different applications in some sense. Would the idea then be that, I mean, would you kind of think about introducing another fee market essentially for, like operators to kind of share state and settle transactions across, like state that is kind of uncharted?
That, like, I could not, like, we don't have this design yet with the decentralized operators, and we don't have fees yet. So, yeah, but it's like something I guess we definitely need. But I cannot, unfortunately, answer the question right now.
Okay, thank you very much.